Hi everybody, thought we might do an example torque problem, a little more complicated than your basic teeter-totter, but also very useful for understanding torque. Okay, here's the basic setup. We've got a wall, and then we put a hinge on the wall, and then we got a bar of some like a pole or something that's stuck onto the wall. So that's this bar here. And then to keep it from flopping over, we're attaching a wire to it. So this wire here is attached at the wall and in there. And this example problem you might recognize from the WebAssign homework. So what do we do about this? So actually, beyond the setup, I forget what the question is even asking. So let's just make up a question, which is let's see what the tension is in this wire. So that's the question. What is tension in the wire? And we should be given other things. So like the mass of the bar. Hey, well, I'm making this up. Let's make it easy. So let's say it's a kilogram. How about the length of the bar? Length of the bar, 1 meter. How about the uh, angle? Actually, I remember that from the problem. So the angle theta was 25 degrees. All right, let's see how far we can get with that info there. How do we approach this? Well, it's a statics problem. It's not moving, so we have two things we can check. We can check that the net force is 0 and also the net torque is going to be 0. So those are our statics equations that we can use to solve problems. So for forces, let's go ahead and figure out what the forces are. So there's going to be gravity. And maybe that's the subtle thing, I don't know, but for gravity what we do is we take the middle of the bar and we call that point the center of gravity. So that's a little trick that appears here and there. And so we're going to have our weight vector. It's going to be pointing down from there. And of course, weight is always the mass of the bar times the acceleration due to gravity. So that's one force right there. And the other force is in the wire. The wire has some tension force in it. It's attached to the wall and the bar both. So but the only direction that a rope or cable or wire can, the only direction that's valid is along the wire. So we're going to have some force vector, but it's got to be along the wire, and we'll call that capital T for tension. Okay, so what else? Because that doesn't look quite balanced, does it? We've got a left force and a down force, and if those are the only forces, then that's not static. So the other forces needed to balance that have to come from the other attachment point. So we got the bar here. It's attached to the wire up at this end and the hinge down at this end. So the hinge forces have to balance those other guys. So to balance the weight downward, there must be a force upward from the hinge like that, and there must be one to balance this tension that is pushing the bar back out. Since the tension is going into the wall, there's got to be another guy here. So I don't know what to call them, Fx and Fy, I guess. So the components are nicely perpendicular to each other. So uh, the tension force in the x direction only must balance the force from the hinge in the x direction only. That's an interesting little equation there. Since we want tension, maybe that's useful, or maybe it's not useful. And then in the y direction, we've got some weight poking downward, and that's got to be balanced by the force from the hinge in the y direction. And actually, we don't know those forces, so maybe this isn't so useful. Those were not given in my little list of variables. So let's see if we can get more progress with the torque condition. Well, let's write down those torques. So what is the torque from the wire? Torque caused by the tension force from the wire. Well, let's look at our definition of torque. Torque is a force times a distance times potentially a sine theta. Whereas I like to put it, it's the tension force times an r perpendicular. So if we go up to our diagram, we've got the hinge is over here. So I guess that would be the distance. We gave that as length. Let's give that a symbol. Let's call it L. Let's call the mass M. Okay, so the length is that distance there. And we have 25 degrees in there, so we should have the same thing here. So there's our theta angle is up in there as well. This guy's your right angle. And then you look at the line of action of that force, which is the tension on the wire, and that's going this way. And so when is it a perpendicular? Well, when that line of action crosses the perpendicular wall point right about there. So what we want here is r perpendicular, is that distance from the hinge up to there. And that is, so we know this, that is the hypotenuse, and we know it's L. So our perpendicular should be L sine theta. So this is a T sine, L sine theta. Good thing I'm using pencil, huh? L sine theta. And here's another question. Is that a counterclockwise torque or a clockwise torque? So you go, oh yeah, it's pushing kind of around the top to the counterclockwise direction, so it's going to be positive. So we'll keep that. What about the other force, the weight vector? I guess torque from the bar, we'll call it. So that'll be the weight force times its r perpendicular, whatever that might be. And right away, let's notice it going the other way. So it's going, it's got a negative sign on it because it's attempting to twist that bar clockwise. And what's its r perpendicular? I guess we can suss that out from the diagram here. So that triangle here is from the center of gravity on down. So our hypotenuse looks like 1/2 L in there. I probably can't quite see that lettering, it's so small. So the hypotenuse is 1/2 L, and your line of force is that from the center of gravity distance there. And so you're actually interested in the distance from the hinge to that perpendicular right in there. And that isn't sign in this case. That is the cosine. So we got a minus W 1/2 L for the hypotenuse times a cosine theta, because it's the adjacent, not the opposite in that triangle. Okay, so that is the tricky business for this this torque equation. Wait, there's more forces, right? There's a horizontal hinge force and there's a vertical hinge force. Oh, but for both of those, the distance is 0. So there is no torque from any forces that are coming from the hinge. Aha, so very good. So our net torque equals 0 equation, let's just take these torque guys, we'll put them together here. So 0 is tension L sine theta minus W times 1/2 of an L times a cosine theta. Is that visible? Good. And it looks like we can divide an L out of that equation. And also let's put this negative quantity over on the other side. So we have a 1/2 weight cosine theta is equal to tension times sine theta. And we can solve for tension. So tension is 1/2 weight. And then we got a cosine theta over a sine theta. And if you want to put this in its full glory, I guess that weight is a mass times the acceleration due to gravity, cosine theta over sine theta. And that is the tension. So we have solved the problem without having to look at the net force equation at all. We've done it all with torque. So hopefully that's useful and it will help you with one of the WebAssign homeworks.